We see concrete pretty much everywhere, but this isn't a story about your average sidewalk. Nope. This is a story about pushing one of the world's oldest materials to its absolute limit. It's about a chemical pause button and building the impossible right in the middle of the sea.
Just think about that for a second. The whole question seems kind of nonsensical, right? I mean, concrete is famous for one thing: getting hard, and getting hard fast. So how on earth could you mix a batch, stick it on a boat, and expect it to be perfectly ready to pour a full day later? It just sounds like it defies the basic laws of chemistry.
And here's why that question is so tough. This number you see on the screen, 1 to 2 hours, that's pretty much the standard shelf life of fresh concrete. The moment water hits cement, it's a frantic race against the clock on every single construction site in the entire world.
So what does this race against hardening actually look like? Understanding this relentless ticking clock is honestly the key to appreciating just how revolutionary this whole solution really is.
Okay, so this is how it all breaks down, and man, it happens fast. The second you mix it, that clock is on. Almost right away, it starts to stiffen up, losing its workability. Then you hit the initial set. That's the point of no return. And finally, the final set, where it becomes solid rock. The whole thing is a one-way street with absolutely no off-ramps.
Now, for years, engineers had a little trick up their sleeve called chemical retarders, and these could buy you a few extra hours, which is great if you're, say, stuck in city traffic. But they were finicky, and in extreme heat, their performance just became wildly unpredictable. Not exactly the kind of thing you want to rely on when you're building a billion-dollar offshore platform.
But what if you could just stop that ticking clock? What if you could hit a literal pause button on that entire chemical reaction? Well, that's exactly what a game-changing new technology now lets us do.
So let me introduce you to hydration controlling admixtures, or HCAs for short. These are not just your average retarders that slow things down a bit. No, you should think of them more like a chemical sleep aid for concrete. They work by forming this microscopic protective barrier around every single cement particle, basically putting them to sleep and stopping that hardening process cold.
And the real genius here is in its two-part system. It's so clever. First, you add the stabilizer back at the plant. This is your pause button. It puts the concrete into this dormant state that can last for more than 24 hours. Then, right when you get to the job site, you add the activator, and that is the wake-up call that dissolves the barrier and restarts the hardening process exactly when you need it to.
And you can really see the difference here. With those old-school retarders, you were basically just guessing and hoping for the best. With HNCs, you get predictable, precise control for a full day or even longer. This means you get superior slump retention, which is just a fancy way of saying the concrete stays perfectly fluid and pourable. The bottom line? You get better quality, way less wasted concrete, and suddenly, the ability to plan projects that were once just pure science fiction.
Now, all of this sounds great in a lab, right? But does it actually work out in the real world, under some of the most extreme conditions you can imagine? Well, let's dive into a case study from Abu Dhabi, where engineers put this technology to the ultimate test.
The mission was just breathtakingly ambitious. The goal was to construct a massive new artificial island way off the coast, a critical hub for the region's energy infrastructure. But there was one huge problem. The only concrete plant was on the mainland, a full day's journey by sea from the construction site.
They needed concrete that could survive a 24-hour trip on a boat and still arrive perfectly workable. And let's be clear, this wasn't some nice-to-have feature. This was the fundamental requirement for the entire multi-billion-dollar project to even get off the ground. It was simple: no concrete, no island.
But here's the thing, the challenge didn't stop with time. The engineers were actually fighting a war on two fronts. See, they had solved the chemistry problem with the HCAs, but now they had to face a brutal physics problem: the relentless desert heat.
I mean, during the summer months over there, the air temperatures can soar to 45, even 50 degrees Celsius. That's a scorching 122 degrees Fahrenheit. And as you might know, heat is a massive accelerator for chemical reactions, including the one that makes concrete hard.
So even with that HCA pause button pushed, the extreme external heat could still basically cook the concrete right inside the truck. To maintain its quality, they had to keep that mix below a very strict 35 degrees Celsius threshold for the entire 24-hour journey.
To win this battle against the heat, they threw an entire arsenal of cooling strategies at it. It was incredible. They pumped chilled water and tons of ice flakes directly into the mix itself. They actually pre-cooled the sand and the stone. They used specially insulated trucks. And crucially, they did all the batching and transport at night, just to take advantage of the coolest possible hours.
So, by masterfully combining this advanced chemistry with some seriously clever thermal engineering, they were able to do what many thought was completely impossible, and in doing so, they kicked off a brand new era in remote construction.
And the result? It was absolutely flawless. They delivered batch after perfect batch of high-quality concrete with 0 rejections. Not one single truck had to be sent back, even during the absolute hottest days of summer. It was a complete and total success.
This quote right here from the project report really says it all. This wasn't some fluke or a lucky break. This project proved, beyond a shadow of a doubt, that long-haul concrete is a reliable, practical solution for the real world.
So why does all this matter? Well, because this technology is fundamentally changing what's even possible. We can now build critical infrastructure in places we never could before. Think offshore wind farms, remote research stations, entire islands from scratch. It also makes construction greener by dramatically cutting down on wasted material. It's a real solution to a massive logistical puzzle, and it's quietly reshaping the way we build our entire world.
Which leaves us with a final and really exciting question. For over a century, we've been chained to concrete's 2-hour clock. Now that we can literally pause that clock for days at a time, what does that mean for the future? What truly impossible structures will architects and engineers dream up next?